Today I will present my joint work with Dr. Schur, which is on Lyapunov diagonal stability, and also we work on the extensions of regular types of matrix stability. My presentation is outlined in this form, and after the background and preliminaries, I will present a necessary and sufficient condition for diagonal stability, which is based on Schur complement. And in the third part, I will talk on a new characterization we obtain for common diagonal solution, and to derive this characterization, we define new notion P sets, and also we use an extension of the diagonal stability of a matrix, which involves the Hadamard product. And in the fourth part, this is the extension of regular types of matrix stability through a partition of a set of integers, and this is called alpha stability. And we define here new notions at H alpha set and P0 alpha matrices. And if I have time, I plan to talk on our ongoing work and do some future projects. Now, the motivation behind to study the matrix stability is the study on the system of ordinary differential equation. Now, in this equation, A is a real matrix, and xt and x hat is real vectors. Now, x hat is called the equilibrium for the system, and the central question for such system is, does xt converges x hat for any choice of initial data x0? And in this case, the equilibrium x hat is said to be asymptotically stable. Now, the equilibrium is asymptotically stable if and only if the eigenvalue of each eigenvalue of A has a negative real part, which means the eigenvalues lies on the left open half plane. And a matrix A satisfying this condition is called a Hurwitz stable matrix. So this is the primary motivation to study matrix stability. Now, to study on this subject, we use many concepts from matrix theory. One of them is the positive semi-definite matrices. A symmetric matrix A is said to be positive semi-definite if for any complex vector x, then x conjugate transpose times x is a non-negative number. And if this is positive number for all x, then we call this as positive definite matrix. And these matrices play an important role in the study of matrix stability. And there are two characterizations we use in our work, which is, first one is a symmetric matrix A is positive semi-definite if and only if all of its eigenvalues are non-negative. We already know that the symmetric matrix has a real eigenvalue, and if this is non-negative, then we get positive semi-definiteness. And if the eigenvalues are positive, we call it as positive definite matrix. On the other hand, the other characterization, we check the principal submatrices. If the principal submatrices are non-negative, then it is also this symmetric matrix is called positive semi-definite again. And throughout the presentation, I will use these notations for positive semi-definiteness and positive definiteness. Let me define the positive stability here that we will mainly use. That means each eigenvalue of A has a positive real part. Actually, the motivation I said that it is the study behind the motivation of this subject is to for the constant coefficient system of differential equations, when A has a negative real part, all the eigenvalues of A has negative real part. But we just use the positive real part, but this doesn't have a big change, the big difference, because if A is a positive stable matrix, then negative A is a Hurwitz stable matrix. So whatever we find for A, so for positive stability, this also works for negative stability or Hurwitz stability. So I also refer to as this kind of stability as just stability of a matrix. Now, this stability of a matrix can be characterized by using matrix equation. This is celebrated Lyapunov theorem, which says A is stable matrix if and only if there exists a positive definite P such that PA plus A transpose P is a positive definite matrix also. And this P is called a Lyapunov solution of this equation, this matrix equation here. Now, this theorem not only characterizes stability, but also gives us a new direction to study matrix, study all the matrix stability, and to define new concepts and develop some new ideas here. Now, one of the concepts related with this is diagonal stability. Now, a matrix is diagonal stable if there exists a positive diagonal D, diagonal matrix D, such that dA plus A transpose D is a positive definite matrix. And D is called a diagonal solution here for P. And this is actually stronger than stability condition because we have a positive diagonal matrix instead of positive definite matrix. So it's a stronger condition than compared to stability of a matrix. We also deal with an extension of this diagonal stability just to check to if we have a set of matrices A1 through AN. So if there exists a positive diagonal D that satisfies the AK plus AK transpose D is a positive definite matrix, then this D is called the common diagonal solution of this system, and the existence of a such D is interpreted as a simultaneous diagonal stability. Now, let me give an example about the diagonal stability of a matrix. It's a simple example. Let A is a 2 by 2 matrix, and A is stable because its eigenvalues are 1 plus and minus. I have positive real part. And choosing a positive diagonal matrix, let's say these, the entries are 2 and 1, we get dA plus A2 transpose D is a positive definite matrix here. Then A is a diagonal stable one. Now, I want to compare this result with another matrix, which is B here, which is stable because the eigenvalues are 1 plus and minus I. However, B is not a diagonal stable because any positive diagonal in this, like the D1 and D2 entries are D1 and D2, we get DB plus B2 transpose D has a 0 entry. But this is not positive definite, we know, because the positive definite matrix should have positive diagonal entries. So this is not a diagonal stable matrix. So my point here is both matrices are stable and both matrices have the same eigenvalues. However, one of them is diagonal stable, the other one is not. So diagonal stability, for diagonal stability, is basically a stronger condition. And also, the eigenvalue condition is not like a sufficient condition to characterize to diagonal stability. So we need some more condition. And this is one of the main problems in diagonal stability. Can we show that a matrix is diagonal stable? And also, if it is diagonal stable, how can we formulate the diagonal solution? So we have two main questions here. First, I would like to discuss about the applications here. Diagonal stability has found applications in like mathematical biology, in systems and control theory, and many engineering areas. And also simultaneous diagonal stability itself has found application in interconnected time break and switch systems. And there are many problems in these areas to be solved regarding to diagonal stability. Now, in this part, I will present a necessary sufficient condition for diagonal stability. First, I introduce some notations here. We shall denote the integer set 1 through k with this notation. And I just call this as set k. And A alpha beta, this notation is a submatrix of A, whose rows and columns are indexed by alpha and beta. And here, if alpha and beta is equal to each other, we just call this as A alpha only. So main ingredient we use in our results is Schur complement, which is defined as in 5, the equation 5. Schur complement of A alpha in A is defined here, and A alpha should be non-singular matrix. I would like to illustrate this with a partition matrix. We mostly use that type of matrices here. Now consider partition matrix A. Here B, C, D, and E are block matrices. Now let's say A alpha is equal to B. Then A alpha complement is E, and the other matrices are D and C. Now B is non-singular matrix. If B is non-singular matrix, then Schur complement of A alpha in A is E minus D, B inverse C. Now, this is Red-Heffer's result. This describes a procedure to determine the diagonal stability. Now, here, a matrix, a non-singular matrix, with the last diagonal entry is positive. Now, let's say alpha is a set n minus 1. And A is diagonally stable if and only if A alpha and A inverse alpha have a common diagonal solution. A alpha is, and A inverse, A alpha is, first of all, A alpha is the principal submatrix with n minus first order, and A inverse alpha is also the principal submatrix with the order n minus 1. So, the Red-Heffer actually describes a procedure for nth order matrices to determine diagonal stability. We look n minus first order simultaneous problems here because we need to determine common diagonal solution of two matrices. But the order is reducing here to n minus 1. This result is revisited by Shorten Narendra. Now think about the partition matrix A here. A hat P Q transpose R, and A hat is the order n minus 1 with R is greater than 0. Now A is diagonally stable if and only if A hat and A hat minus PQ transpose R have a common diagonal solution. Now, first of all, the Red-Heffer's theorem, proof is a bit quite lengthy. Now, Shorten Narendra give an alternative proof with using Kalman-Yakovlevich-Popov lemma from Systems and Conservatory. And on the other hand, they restate this result, and without using an inverse here. Now, diagonal stability depends on the common diagonal solution of A hat and A hat minus PQ transpose over R. A hat is A alpha actually in the Red-Heffer's theorem, but A hat minus PQ transpose over R is different than A inverse over alpha actually, A inverse alpha actually. But what is the relation between these two theorems? It's based on two known results. One of them is A hat minus PQ transpose over R inverse is equal to A inverse n minus 1. This A inverse n minus 1 is the A inverse alpha in Red-Heffer's result. But again, they don't use this inverse. They just use the original matrix. And this depends on the result that a matrix A, if it is diagonally stable, shares a common diagonal solution with its inverse. So by using this, another result, they just restate this theorem. Now, we also re-examined this theorem here. We slightly improved the statement, and by introducing the Schur complement. Let me just read the statement here. Now, A is diagonally stable with a diagonal solution D. D hat and X. Now, one of the things we write this diagonal solution here. Now, it is not actually mentioned in Red-Heffer's and Shorten Narendra's result. We here write a D, which is D hat and X, because in the previous result, they only show the existence of this D. However, we give a formulation for this matrix. So we will give a feasible region for X. Now the different thing is Schur complement here. Now A hat and Schur complement AN in A share a common diagonal solution. Now actually the the shortened arandra use a Schur complementer. Now, we introduce here Schur complement because if you just use this formulation, we can obtain many extensions on this theorem. So we will see that after I will give the proof of this result.
I have a question. Can you find always R is positive for any A? Can you
R should be a positive number. It's a necessary condition for diagonal stability. If it is not positive, then it is not a diagonal stable matrix.
Under that condition, you can find always such R.
Oh, they already assume R. Okay, yeah. Sorry, I just skipped that part. Yeah, since R is, thank you very much for the question. R is already a necessary condition. Positivity of R is a necessary condition for diagonal stability. So we include this into sufficiency part here. So
that's another slight improvement.
Yes.
You include this R because they know to be part of the condition. Yeah.
Yes, we include this. Yeah, because this is a necessary condition for diagonal stability. Now we give a shorter and purely matrix theoretic proof. And comparing to previous proofs, this is a shorter and purely matrix theoretic, and this allows many extensions. Now we use two lemma here. First one is used as a procedure to determine a positive definiteness of a matrix. Now, a symmetric matrix is positive definite if and only if any submatrix B alpha is positive definite, and also the Schur complement of B alpha in B is positive definite. And the other one is the Sylvester determinant theorem. If we have two matrices UV and the multiplication is well defined for U and V, then determinant IM plus UV is equal to determinant IM plus VU. So these I's are the identical matrices for given order. Now, necessity part is same, so I just omit this part. I only discuss about the sufficiency part. So our assumptions are A hat and A hat minus PQ transpose over R has a common diagonal solution, and R is a positive number. So from the definition of diagonal stability, let's say this matrix is B, dA plus A transpose D. We need to show that this is a positive definite matrix for some x greater than 0. Now, from the first lemma we use to determine positive definiteness of this, we have an information here, which is if alpha is the set n minus 1, then B alpha is a positive definite matrix here. So in this case, this problem reduces to check that positivity of this number which depends on x, which is 2xr minus the other term, which is P transpose B hat x Q transpose M inverse and x so on. So here fx we just say that this depends on x, or we define a function here fx. We need to show that this function is greater than 0. The first observation here, now M is a positive definite matrix. So that means M inverse is also positive definite. So the second term in the fx is always a non-negative number. It's actually, if this vector is not, if it is not 0, then it's always positive. But if it is the 0, then we get a 0 value. So it's always non-negative. We know that R is positive from assumption. Now, whenever x is smaller than 0, this fx is smaller than equal to 0. So this is the first observation. And on the other hand, if we expand this term in the second term in the fx, we get the quadratic expression. Now, our main question here is if there is the x greater than 0, that makes fx is greater than 0. We are looking for this. And this is a quadratic equation. That means this the graph of fx should crosses the x-axis. And if it crosses, that means it happens in the non-negative part of the x-axis. So we need to show that the discriminant, and this is actually the positive multiple of the discriminant. So discriminant should be positive number. So we are looking for like delta if it is positive or not. Now we write this delta here as a determinant of 2 by 2 matrix. Now here we need to show that this determinant is positive. Now in the diagonal entries we have r plus, negative r plus something, so we just pull out these r's and we obtain another term here, r squared times determinant I2 is 2 by 2 identity matrix minus a matrix multiplication. So we use now here Sylvester determinant theorem. That gives us, if we change the place of the matrix multiplication there, we get here I m minus 1 and minus some matrices there. And if you continue with this delta, we finally arrive delta is equal to r squared times determinant m inverse times determinant d hat s plus s transpose d hat. S is the Schur complement of an in A. This is a positive number because r squared is positive. Determinant m inverse is positive because m inverse is a positive definite matrix. And the other determinant is also positive because d hat is solution for Schur complement of an in A. So we finish the proof here, and from the proof we can also specify all feasible regions of X. So this gives us a formulation for the diagonal solution D. D hat is already known, and we are looking for X. Now, in the proof we check the quadratic function. So, and we show that the discriminant is positive. So that means there are two solutions coming from this function. What I mean is two zeros of this function. So x1 and x2 are the zeros here. And if the x here, any x, falls in this interval, we get a diagonal solution D. There is an issue here. If Q is a zero vector, then we just say that x2 is just infinite, positive infinite. And if in this case, that we can always find, because this x1 is a positive number here, and I'm sorry, there is a typo here. There is no negative value here. I'm sorry, but this is just a p transpose d hat m inverse d hat p over 2r, and between this number between infinity we can always pick positive x value. Now, one of the corollary of this result. Now we use Schur complements, and this Schur complement is on the last diagonal entry of this matrix. Actually, we can extend this to any diagonal entry. Now, if we choose a diagonal entry on the matrix A, let's say in the k position, if AK is positive number, then let's say alpha is the set n minus k, and A alpha and the Schur complement AK in A share a common diagonal solution, gives us the diagonal stability of the matrix A. And this result based on two other results, which is the diagonal stability of a matrix A is preserved under simultaneous the row and column permutations on A. And another result is if a matrix A is diagonally stable, then any Schur complement A alpha in A is also a diagonally stable matrix. Another corollary here we get from the proof is we extend the Red-Helfer's result here to set of matrices to share a common diagonal solution. A1 through An is given, and they are partitioned in this form. Now, we are looking for a common diagonal solution in the form d hat and x. Now, the first condition is all rk should be positive. Second condition is again the submatrix A hat k and the relevant Schur complement A n in AK for all of these matrices, these two matrices coming from all of these matrices, so they all should share a common diagonal solution we had. And on the other hand, we need the third condition here. This third condition actually is similar to the solution of X. So we need to satisfy that here. All solution intervals coming from each matrix should intersect. So here, maximum of x1k, if it is smaller than minimum of x2k from each matrix, is numbers coming from the solution interval for each matrix. So if this is smaller than x2k, x1k is smaller than x2k, then we can choose x from the interval between the values between x1 and x2. So here basically this problem actually reduces the problem in n-2 case. For example, we have a 4x4 matrix. We are looking for diagonal stability. Should the first result reduce this problem 2 matrices on 3x3, order 3. Now, if we apply this corollary, we are reducing the problem 4 matrices with order 2. So, for any order, if we start, we end up with the order 2 actually, which is the base case for applying the first result. So here, but the main question, what about 2x2? Can we just obtain some characters like algebraic conditions or explicit conditions only? Because this third condition is depending on the hat here. So this is the main difficulty. We need to choose a good d hat to satisfy the third condition. Now we work on also the 2x2 case, which is the base case. Now we have 2x2 M matrices. We are looking for a common diagonal solution in the form D1 and X. Now, these matrices share common diagonal solution if A1 through AM are all P matrices. That means they are 2x2, right? So the diagonal entry and the determinant of these matrices are positive. Second condition is the third condition of the previous corollary. If we have a solution interval from each matrix for X, so which is x1k and x2k. So if we take the maximum of x1k, this should be smaller than minimum of x2k. Now, the good part here is the x1k and x2k depend only on the matrix entries. So this gives us explicit conditions for characterization of the M 2x2 matrices. This result is also the extension of another result given by Oleng and Narendra. They only prove this result for pair of 2x2 matrices. We extend this to check that if for any number of matrices given, then we can just apply this corollary to find the common diagonal solution. And x can be chosen from the interval x1 and x2. Let me give an example on common diagonal solution problem. We have 3 matrices. Sorry, we are looking for the common diagonal solution of these matrices. Now, our corollary here reduce the problem here 6 2x2 matrix. What are these 6 matrices? One of the while taking alpha is just set 2. These matrices are the principal submatrices A1 alpha, A2 alpha, and A3 alpha, and the other matrices are the relevant Schur complements here. So these 6 matrices are 2x2. So that means we can apply our result on 2x2 matrices, and if we have a common diagonal solution in the form D hat, which is 1 and x. Now x, we find that we obtain an interval here for x. Now remember the corollary has another condition. We need to we have solution interval for all matrices coming from all matrices. These intervals should intersect. Now we choose an x here. X is between like these two numbers. We choose x is equal to 0.9. And we construct a common diagonal solution here, D. D hat and y. Now I apply the corollary here, and we again obtain an interval. I would like to briefly discuss here. The choice of x is important here, and this is the main difficulty of this problem. Now, actually, we are also working on this problem. How can we choose a good x that satisfies the third condition? So, I mean, that doesn't mean that to move to third condition, that doesn't mean that any x satisfies the third condition. So this is the main difficulty of the diagonal stability problem. So here, yeah, we of course choose the x that works for here, the diagonal b works here, and if y is in this interval with 0.604 and 0.71, then D is a common diagonal solution of A1, A2, and A3. So any diagonal solution in this form is the common diagonal solution for these matrices. I would like to visualize this on the graph. Here we find that solution, so diagonal solution D. Now let's look at this matrix Qi, which is DAI plus AI transpose D. We need this matrix with a positive definite. That means all its eigenvalues are positive. So let's look at the minimum eigenvalue, smallest eigenvalue. Now the diagonal matrix depends on y values. The interchange of y values, we just draw the graph of eigenvalue here, the smallest eigenvalue. And as we can see, if y falls in the interval we find in the previous slide, 0.604 and 0.71, then all of them have the positive eigenvalue here. If y doesn't fall here in this interval, and any value we like in the out of this range, that means D is not a common diagonal solution. So this is the graph of the smallest eigenvalue here we find. In the next section, one of our work is to obtain a theoretical characterization for common diagonal solution. Now here, let me first give this theorem, which is diagonal stability, characterization for diagonal stability due to Berker, Diamond, and Clemens. For every non-zero positive semi-definite x, a x is a positive diagonal entry. This is very interesting connection between diagonal stability and the set of positive semi-definite matrices.